Hi everyone, my name is Chuang Gan, a researcher at MIT-IBM Watson Lab. Today, I'm very excited to share our recent work on multimodal intelligence. As we all know, with the emergence of deep neural network, we have witnessed revolution on many single modality tasks, such as image classification, video recognition, machine translation, and also speech recognition. In the meantime, the community also made considerable progress on many multimodality applications, including visual captioning, visual question answering, visual grounding, and also visual reasoning. But most of this success are built on visual content understanding. Later work has been studying how to understanding the causal structure of the visual world. Let's take this toy video as example. When humans look at this video shown here, not only can we describe the event that happened, but can also reason about the causal structure behind the event, make prediction about the future, and even imagine unobserved counterfactual scenarios. We believe a smart AI system should not only solve the pattern recognition problem, but also have the ability to capture the cause and effect in the physical world. So towards this goal, in collaboration with MIT, Harvard University, and DeepMind, we built a new video understanding dataset named as Clever. We want to push the boundary of temporal and causal reasoning on video. Video Clever dataset consists of 20,000 synthetic video and around 500,000 questions with well-controlled bias. It also provides ground truth annotations of video state for model diagnosis. The question includes 4 different types of tasks focused on causal reasoning, including descriptive, explanatory, predictive, and counterfactual. Let's now take a look on some examples of this dataset. Among the 4 type questions, descriptive questions ask the agent about the event and that happened during the video. For example, we may ask the question, what's the material of the last object to collide with the science cylinder? The answer should be metal. For the explanatory task that the model needs to explain the cause of a specific event by choosing another event or object that is responsible to it. In this example, the collision between the rubber sphere and the science cylinder pushed the cylinder to make another collision with the other metal cylinder. Therefore, we regard the second collision to be caused by the first. Predictive question query about the future event after video terminates. In this example, the metal sphere will keep moving along the white rail and collide with the red sphere. So the answer should be the second. Counterfactual question requires the model imagine the outcome when object is removed from the center and select the event that will happen under the unobserved scenario. For example, when we ask question, what will happen without the science cylinder? The answer should be the second one. The red rubber sphere and the gray object collide. We evaluate the performance of a wide range of baseline models, including the currently set up model on video QA dataset and also on image Clever dataset. While the MIC network achieved more than 85% accuracy on the descriptive question, it performed very poorly on the remaining explanatory, predictive, and counterfactual tasks. We believe to solve this task, a model is required to using structural object-centered representation and implicitly capture a dynamic of video internal state. Based on this observation, we propose a new model called Neuro-Symbolic dynamic reasoning, which uses structural visual and longer representation to track the changing of causal video reasoning tasks. Our model first parts video frame into an object-centric structural representation that includes the position information and static attributes, such as color and the shape of each object. Then we send this representation to a dynamic model to predict the object trajectory across different frames using a graph neural network. The input question is passed into a program representing its underlying logic by the sequence-to-sequence network. Finally, the program is executed by a symbolic executor on the predicted motion trajectory to output an answer. Let's look at an example of an SDR model perform counterfactual reasoning. Here, the upper window shows the input video, and the lower window shows the predicted trajectory when science cylinder is removed. You can observe that our model is able to capture the counterfactual event without observation and answer the question properly. We also show quantitative evaluation on this flow chart. You can observe that our model improves the performance on clarity, especially for more challenging explanatory, predictive, and counterfactual questions. This result shows that the implicitly structured representation and the dynamic model is an essential part for solving this kind of challenging task. Okay. In the second part of the talk, I will talk about another very interesting multimodality application. We call it vision and sound. Actually, intensive evidence from cognitive psychology and neuroscience has suggested that for young babies, though they have very little knowledge about language and concept, but they can still capture the correspondence between different modalities to arrive at a deep understanding of the physical world. For example, in this video, so you will see you will see a baby that is doing something that we feel is a little bit random, hanging cup together, making stack, knocking them down, and hearing the character. But actually, this kind of multimodality is the key that to lead the development of many interesting behavior for a young baby. And inspired by this fact, we are interested in building a system that can see and also hear. In the remaining part, I will show several exciting applications that our team has been working on to connect vision and sound. The first application I would like to introduce, we name it as visual sound separation. The task is that, give a music performance video like this. Our goal is to separate the sound source played by different instruments. So before going into any technical detail, I want to first give credit to my colleague, Dr. Hang Zhao and Professor Antonio. Actually, we started working on this vision and sound application 2 years ago, and we built the first visual audio sound separation system called the Sound of Pixel. I think many of you guys have already played the cool demo on the website. And later we found that only using visual appearance feature is quite limited. Then we introduced optical flow and trajectory-based motion representation that can further improve the visual sound separation result. The very impressive performance on the task that we still found the visual conditions are not strong enough. Especially when we're separating multiple instruments of the same type, like this example. So it's clearly that our model even incorporates some motion feature can did nothing in this very challenging case. So to address this issue, we propose music gesture, a key point-based structural representation to implicitly model the body and finger movement of musicians when they perform music. The key idea here is that we want to using the body language of musicians to help visual sound separation. Actually, our network consists of 2 components. The first one is the video analysis network, and the second part is the visual audio separation network. The video analysis network first take a video frame to extract global context feature, and then we extract human body key point coordinate using OpenPose API. And the graph neural network is applied to integrate the body dynamic cues. And then we combine the appearance feature and the key point dynamic feature as visual conditions. Finally, we apply an audio-visual fusion model to associate with body movement with the corresponding audio signal to achieve the visual sound separation. Okay, now let's watch some demo video to appear the result. And first, I will show some baseline result, and later we will show our new music gesture result. So this result is generated by our previous sound of motion system. It can be found that actually the system almost did nothing for this kind of very hard case. But instead, that when we're using the body language of musician, we can do pretty reasonable job that we can watch the video next. Yeah, so it's not very perfect, but we can feel that it still significantly outperform the performance of previous system. And I will show another example. So again, the previous sound of motion system failed in this case. And let's see the music gesture. Okay, lastly, I will show an example actually I like most on a very challenging piano duet separation. Again, the sound of motion doing nothing. And how about our system? Yeah, it's pretty reasonable result. Our results, our success is not only limited for duet sound separation, we also achieve significant success on the multiple instrument sound separation. I will show a demo here. Yeah, it's pretty reasonable good. Our structural key point representation also have another benefit that it can also enable us to isolate the sound of body part. I mean, I will show example that a musician make two kind of different sounds. using different body parts, but our system can also do a good job in separate different sound components. Okay, after watching this video, I think you will have a question that we can do very good sound separation, but can you try to generating a piece of music based on body motion? The answer is yes. So in a following up paper that we published on this year ECCV, we proposed a new system called as Foley Music. That we given a salient music performance video. The AI model can generating a reasonable synchronized audio. Well, actually, this is a pretty challenging task because I mean, so when you want to generating visual aligned video, I mean, the first challenge came to mind is that you need to recognize the interaction between instrument and the music players. And secondly, you also need the audio representation that can respect the basic music rule and also easily to be predicted from vision. Finally, we also need the model to associate these two modalities. And to address the challenge, we identified two key elements for a successful video-to-music generator. For the visual perception part, we track key points from video frame to implicitly model the body and part and hand movement. And for the music, we propose using MIDI representation to encode some basic knowledge about, to encode the structural knowledge about the audio part. So I think in computer vision community, many people are not very familiar with the MIDI event representation. Here I give a brief introduction. The MIDI event actually is encode timing and loudness information for each note event. It's a symbolic representation, and the note event includes some note on or note off event. So given a pair data of body key point and automatically treated MIDI event, the music generation from video can be posted as a motion to MIDI translation problem. So concretely, in our model that we first extract the body key point and then apply graph DNA to the detected key point to capture body dynamic. This part is actually similar to the music gesture paper. And then we're using a transformer to align the key point feature with the MIDI event. This transformer is an autoregressive model that it can automatically align the temporal it can align the temporal information between the key point and the MIDI event and enable this kind of music generation. Finally, the MIDI event can be converted to the waveform with a standard audio synthesizer, and then we can listen to the very realistic music here. Okay, I think all you guys want to watch some music generation results. So let's do it. So since another benefit of MIDI representation that is fully interpretable and transparent, so it will enable us to perform music style editing very easily. So I will show some video demo results as well. Okay, let's go for another example. Okay, so in the half of my talk, I talk about is most about how we can utilize the multimodal cues from a passive video dataset. And in the remaining talk, I will discuss another topic I think is very hot recently. It's about how we can using the multimodal information for embodied AI intelligence, embodied artificial intelligence. The first application I want to talk about is we name it as the audio visual embodied navigation. This work joined with my another advisor, George Tenenbaum at MIT. So here we focus on the problem that we how to teach an intelligent agent equipped with a camera and a microphone to interact with the environment and find the sound source in a multi-room apartment. So we name this task as audiovisual embodied navigation. As you know, this is a brand new task. So we first have to build a multimodal virtual environment for this task. And so we built this platform on top of the AI2Solve platform, which contains a set of scenes built by using Unity game engine. And we further incorporate a special audio toolkit, Reason's audio API, into the Unity game engine to simulate the sound effect. And also there's the agent that with a microphone and camera that can interact with environment and his goal will be find a sound source. For the visual scene part, the AI2Solve platform actually already provides many near photorealistic indoor scenes. But the main limitation is that the room provided by AI2Solve are isolated from each other. Thus, it's not very suitable for the audiovisual navigation task because in the task we want to reason about the room layout and how you go out of the video, how you can go out by room to find the sound source in another room. So essentially we need more complexity. So to address this limitation, we mainly concatenate several rooms into a multi-room apartment. And we also divide the apartment into grid world for the ease of quantitative evaluation. For the audio agent that's be using open source Reason's audio API, which can accurately simulate how sound wave interact with human ears. In the audio engine, that it contains a special audio SDK that can create high fidelity spatial sound in a virtual environment, and also support acoustic retracing according to the geometry of object and room. Thus, we can use this module to provide the agent with the sound stream. Okay, here let's watch a demo to prepare this environment. In this environment, we can see the two setups for seeking the sound source. In the first setting, we let agent that can conduct two stages of interaction. The first one is random iteration. The second part will be the goal-directed navigation. During the iteration stage, the agent can randomly walk around the environment and until its trajectory budget line, its trajectory lines reach a given budget. This iteration appearance can be used to build an internal world model of the environment. And in our proposed solution, actually, we build a visual mapper using a key value-based spatial memory, where the key is the visual observation of its video state, and the value contains the location coordinates and the action taken by the agent. So based on this iteration and the spatial memory, actually, we can easily construct a partial graph representing the connectivity of the room. And in the second stage of goal-oriented navigation state, we first retrieve the top 3 memory slots that closest to the agent with observation. And then we can use this retrieval result to estimate the absolute location of the agent. Because in the memory, we also store the coordinate of the agent, so it's very easy for us to track this kind of information. And after that, the agent leveraging the sound perception module to estimate the direction and the distance of the sound source based on the current location. And finally, the agent can plan to find a short path to reach the goal based on, the partial map and also the inference from visual and sound perception module. In the middle of navigation says that the dynamic path planner can also update the path based on any new visual and audio observations. Okay, so in the second setting, we consider more challenging task. There's no exploration allowed, so the agent must build a special map of the environment and also navigate through the environment. Need to combine the task together. To address the challenge, it should be introduced a visual perception mapper that is consists of a dynamic partial map while the agent navigates through an environment. So the dynamic partial map represented as a top-down 2D occupancy map about the grid world environment. Each entry tree of this map represents the agent's belief about whether this grid can be transversed or not. The starting position of the agent is at the center of the map. Since the agent only has access to the visual observation of the nearby area, so the visual perception mapper produces a local occupancy map in front of agent at each time. So the agent then can upload the global occupancy map based on their local occupancy map and be using a Bayesian rule to update this kind of global map. And once the dynamic partial map is constructed, the agent can easily using a similar planning-based approach to find the shortest path to reach their goal. In order to show how well our model generalized to new target and new environment, we consider 7 baselines to compare with. From this table, we can find that the proposed audiovisual agent outperform all other baselines across all metrics. So this result indicates that our system is better to leverage the layout of room and also better combine with visual audio perception model to find a short path to reach their goal. And we also observe that the performance of border-free, such as A3C-based approach in our memory is slightly, is significantly worse than the result reported in previous literature. I think the main reason is that in this evaluation, we mainly focus on generation. So we're putting the agent in previous and same environment. Actually, it's much more challenging, but also very realistic because in many real applications, we cannot imagine that the agent cannot adapt to any environment, that he has to learning to working on every environment that to achieve this kind of sound seeking abilities. Okay, so here I will show a demo about agent behavior and how he leveraging his visual and audio perception module to find the sound source. Okay, so the last part of my talk, I will introduce our recent work on the exploration of multimodal reinforcement learning. So there's a paper we recently archived named as Noise Agent Self-Surprise Exploration by Predicting Outer Events. So to start with, maybe we can watch to a target game. Okay, I think when you're watching the video, many people might have the same feeling with me that we will not only notice the visual state change, of the environment to understand the rule. But we also leveraging the sound effect. I mean, because the sound tells us a lot of information about this game. For example, that sound tells us there's a bad reward, and when we take some good action, that we earn some score. That there's also some event tell me, tell us actually that this is a positive one. So actually, the sound effect conveys a lot of useful information. So a natural question arrives at: can we utilize the sound effect to guide our operation? So actually, the fact is not only applied to the to the entire game. It's also applied to many real-world applications, because in many cases that the occurrence of physical events, such as objects coming into contact with each other or changing state, often correlated with both visual and auditory signal. In AI field, however, much more attention has been paid to the way of the visual signal, for example, the pattern change in pixel, that we use that to drive learning. But we believe that audio effect, the sound information also is another important structural information that the machine learning should deploy. As compared to the visual thing, actually sound offers more directly and easily observable consequences of action and interaction. So if we can better leverage them, we can do a lot of interesting tasks here. Based on this motivation, we propose auditory event prediction-based operation framework. And concretely, our framework consists of 2 stages. The first is sound clustering. The second one is auditory event prediction. So we first need to collect a small set of diverse auditory events and use them to define the the underlying auditory event classes. And to achieve this goal, we first train a policy that rewards the agent based on the whether they make a novel sound. And then we run a k-means clause. We run a k-means algorithm to group the data into several auditory events. Here we visualize some auditory events that are discovered by this kind of k-means algorithm. We can notice that the image under the same cluster indeed contain very similar events. So in the second phase, we need to train a forward dynamic model that takes input as embedding of visual observation and action to predict which auditory event will happen next. The prediction answer actually can be used as an intrinsic reward. To encourage, in this intrinsic reward, we encourage the agent to explore this auditory event with more uncertainty. So in this way, that the agent can learn more about environment and building better causal model about the field work, and it will inherently learning many useful skills. Okay, let's take a look on the EPR result that we compare with some vision-only operation system. We compare the result on the Atari, we conduct appearance on 20 Atari games, and we compare with several SODA vision-only operation approach, such as SML, ICM, R&D, model disagreement. So this is all only based on vision. But we can find that our audio-driven strategy actually can learn more eternal reward than previous system. And to be noted that in this appearance setting, we only train it with intrinsic reward because we want to only understanding how the intrinsic reward will get very interesting behaviors and lead the agent can actually master very useful skill. Actually, this is very new. It's almost the first work using a sound effect as an intrinsic reward. We believe that this observation can inspire more work on multimodal IR operation. Here we also visualize the relationship between intrinsic and extrinsic reward to understanding why our model achieve such compelling result. we can find that the action reward and interest reward actually align very well in this kind of iteration game. That this is the essential way why we can using this kind of audio signal to achieve very promising results on the entire game. And here we also visualize the agent behaviors of different agents. We can find that our knowledge agent using audio effect actually can exploration environment more faster and also earn more eternal reward. In this kind of game engine. So actually, our model, our audio-driven model is also complementary with the visual signal. It's not, the audio signal is not a different method, but we can definitely combine with many audio, many vision-based exploration methods. And also we indeed find that in some environments that the sound maybe in some entire game that there's a lot of background music and noises that the sound signal is not very robust. We can definitely combine with the visual signal here to further advance the setup. So there's a lot of room that we can play with in this kind of multimodality R operation. There's a lot of exciting work that happened in the audio visual learning. But we also noticed that there's, especially for this kind of audio visual embodied task, there's not so many environments or data sets that we can play with, and most about this kind of toy or 2D, entire game. It might not actually reflect the real many real application in physical world. So to address this issue, actually, I think it happened last month that we released a new 3D world multimodal platform for interactive physical simulation. So actually, we spent close to more than 2 years and working on this kind of platform. And we recently make a strong push to open source this platform. And the benefit of this environment is that we can simulate high fidelity audio visual data in many complex physical scenarios. So maybe we can watch this video to experience. This is just one example that we want to show the power of this agent that you can generating photorealistic images and also the land physics-based sound. I want to mention, so I want to emphasize here that different from the audio-visual navigation task that we using environmental sound. Here we can we can generating impact-driven sound that's based on the physical property and the collision information between objects. So this will enable many new applications on audiovisual embodied learning. And again, that we already open source the code and also this platform. So if you want to use this one, definitely have a try. And also, if you feel there's anything is not tailored for your application, you can email us and reach out to us to tell about what you're thinking. And we are happy, to incorporate, your suggestion. So actually, when we building this kind of TDW framework, we hope to be, we hope it to be a general purpose, but it could happen that it's not meet your specified application. But definitely reach out to us, and we are happy to provide some feedback. Okay, I think I'm running out of time, and I would like to thank again for the organizer to invite me here, and I'm happy to to take any additional question in the following section. Okay, that's all. Thank you.